Welcome to the EPG Pathshala lecture series for postgraduate students in architecture. The subject we are discussing is sustainable and green building design, and the module we'll be delving into is environmental architecture and climate related issues part 2. So if we look at energy efficient design and processes, we have to make sure we have the climatic zone of the site. We need to adopt passive architectural design, reduce the hard paved area. We need to retain mature trees and use of low energy or passive heating or cooling. So we need to make sure that the whichever climatic zone that place is in, we keep that into consideration. We take into consideration even the microclimate of the site, because the microclimate could actually change because of having a river or a pond or anything within the site. Passive architectural design refers to anything that we are actually going to have a sustainable type of design and reduce the concreted paved areas. And like we have already discussed, let's reduce the number of trees that need to be cut down before we move on to the construction and design phase. If you look at the design strategies in hot and dry climates, you need to have large openings, great window area, internal courtyard for cross ventilation and thermal buffers, radiation barriers in the form of canopies, chhajjas, verandas, etc. So if you look at in hot and dry climate, what happens over here when you have a window? If you actually have a properly designed chhajja and fins, it helps to keep the interiors cool, because anything that cuts in, it gets cut, any sunlight that comes in, and hot air, as we know, rises. So in the interior, when hot air rises, it can come out and the sunlight will not enter the space. So if you look at the chhajja over here, the entering angle and the exit angle, when you have the projection over there, the sunlight cannot enter and you will only have daylight entering the space. So over here you have grass, and which absorbs heat and minimizes radiation. If you had a concreted space here, or even stone for that matter, it will actually re-radiate and it will enter the house. So we need to make sure that we have plantings and landscaping wherever possible rather than any hard paved surface. Design strategies in warm and humid climate. Orientation should be preferably in the north-south direction. It needs to provide maximum cross ventilation in the building. The design strategies we need to take into consideration in warm and humid climate is we have a prevailing summer wind, and like we discussed, it needs to be north facing or south. Vegetation gives shade from any kind of western sun but does not block the breezes. So if we have north, we need to make sure the west is blocked, because west is where, as the sun sets, we have a lot of heat coming in from there. We need to have open areas around with a veranda for cross ventilation and an open plan for living area. Tall palms do not block the breezes, and a main veranda on the windward side of the house. And we need to have steps to high set the house or tilt the house, which means that you're going to bring in air and breeze into the house. If you're not going to raise the height of your house, you will be having all thick cluttered air along the ground floor. So as you raise the level of your house, there is more breeze and the vegetation that is there around will help move the breeze around. Design strategies in composite climate. Plan the building around the courtyard. Reduce heat gain in the building through the building envelope. You need to plan water bodies, cavity walls, terrace gardens and light shelves. So you need to have cross ventilation at the micro level through the openings. So you have a courtyard, and that's one of the important factors that we need to see. You need to reduce the heat gain by having sure that you have a building envelope that is not continuous and there are gaps for heat to escape as well. Design strategies in temperate climate. You need to have cavity walls, terrace gardens, green roofs and light shelves. Roof insulation using insulation materials like china clay or clay pots is advisable. Moving on to design strategies in cold climates. Glazing windows up to 25% of floor area. double glazing to avoid heat losses during winter nights, using sun spaces, and adopting trombe walls. So, this is an example of a trombe wall. If you look at over here, this is a modified trombe wall where you have the cool air entering, cool air settles down, hot air rises. So, you have the cool air that any house that will be there, it will have, it will exit, and the glazing that is there will actually insulate it, and the concrete wall with a stucco finish. So, then the sunlight is right there outside, the warm air will rise, this air will get heated because of the glazing. The glazing over here will make sure that the cold air gets warmed up, warm air will rise and will enter the house, and that will warm up our building. And then we need to ensure that we have a sloped roof as well, so that any sunlight that is there will hit the roof rather than directly being re-radiated. So, we need to ensure that we use all of these elements successfully to reduce the consumption of electricity and have a very passively well designed building. So, how do you go about designing for a cold climate? You need to have a completely different approach to design and respect for the weather. Buildings must be designed with an environmental barrier. You have to be more concerned with their heating season rather than the cooling season, because in cold climate the summer season is relatively much smaller or a much shorter period. So, if during the summer months or a couple of months they do require electricity to keep the building cool, it is fine, because the majority of the year the climate is going to be cold, and we need to ensure that the heating season does not consume a lot of electricity. So, within the realm of the seasons, we need to choose the better of the two options and go ahead with that design. If you look at the building envelope, the building envelope is basically decides the consumption of energy by the HVAC system, let it be because of excessive heating required or cooling required. So, reduction in energy consumption by the HVAC system, the thermal energy efficiency of the building, internal heat gain factors, you have a solar heat gain coefficient or SHGC. The lower the SHGC, the lesser the direct incident heat gains from the glazing surfaces. So, now if you look at strategies for designing building envelope, we have the two synonyms described, the two acronyms described over here. WWR is window to wall ratio, and here we again have the solar heat gain coefficient. So, we need to keep this in mind with respect to what percentage of the walls we are going to have glazing and what is the solar heat gain ratio of coefficient of that place. So, depending on the climate our area is in, we have readily tabulated facts that we can directly follow. The comfort zone. Now, this is something all of us use very frequently when we talk. When we talk of a building and design a building, what exactly, irrespective of the building being in a cold climate or a warm climate or a hot and humid climate, the comfort zone for human beings relatively remains the same, around the same region. Of course, people are certainly acclimatized in those areas to a different kind of comfort zone. For instance, people in India will call a particular climate warm and not so hot versus a person from, say, Netherlands coming to Chennai and finding the Chennai weather extremely hot. So, within the realms of those possibilities, the human comfort zone relatively remains the same. We have a particular temperature zone range that we are comfortable in without any additional warm clothes or, say, comfortable clothing that is usually used. Then we have the deciding factor of, say, there is no air conditioning or no heating devices. Then there is also the thing we need to talk about, different climate types. Different climate types will suggest different comfort zones, and based on that we need to decide what kind of design we should go ahead with. So, comfort zone refers to the range of temperature, conditions of air movement, humidity and exposure to direct sunlight under which a moderately clothed human feels comfortable. This will definitely vary when we are considering outdoor versus indoor conditions. Also, this will vary because of different climatic zones like we just discussed. This will be different for different cultures, combined with different climatic conditions, what are those people used to in the general sense? As architects, we use our buildings to not only create comfortable indoor environments, but also pleasing, useful spaces outside our buildings. So, you need to have a range of comfort that we need to design within. So, outdoor, indoor comfort also has to be taken into consideration. It's not like you can wear out loads of clothes and enter a building, and when you come out, you have to remove all the layers. So, your building, like we discussed, has to be like a moderator. It has to be just a transient space for the user from the exterior environment. This is from a famous illustration, Design with Climate by Victor Olge. This is the finite point of expected comfort for 100% mechanical heating and cooling. So, if you actually look at this diagram over here, it's like a graph. So, we have a particular cold place as well as a hot place, and bang in the center within this green area is what we will define our comfort zone. So, right here we have up to 37 degrees C, here we have a 15 degrees C, and here we have right from the temperature we usually call. So, here we have the cold temperatures and cold climates. Here you have the hot temperatures and the hot arid regions, sultry, humid areas and all of that. And this belt is considered our comfort zone, anywhere from 21 to 26 degrees C, 28 degrees C actually, depending again within that climatic zone. Our humidity, again, we are usually it's considered up to 60%, up to 70% is considered a part of a comfortable humidity that we can constantly bear. This is a schematic bioclimatic index which gives us an idea on how we can go about reducing the operating energy. So, by making sure our design has a comfortable temperature maintained, however the passive design is, whether it's passive heating or passive cooling, we can ensure that we are reducing the energy consumption tremendously. So, here we have an example of the passive bioclimatic design, how we reassess the comfort zone. This again is the computer science building in York University in Toronto. Comfort expectations may have to be reassessed to allow for a wider zone, that is characteristics of buildings that are not exclusively controlled via mechanical systems. Creation of new buffer spaces to make a hierarchy of comfort levels within the buildings. It requires a higher occupant involvement to adjust the building to modify the temperature as well as airflow. Moving on to microclimate. When we design with the specific local environment characteristics in mind, we have to actually manipulate the relationship between climate, the site and the building to create a local environment or a microclimate around the building. Now, if you look at even a city like Chennai, which is quite a vast metropolis, the temperature currently, if you just take at one point of time, the temperature will change between Mount Road, it will change in Vandalur, it will change in Adayar, it will change in Old OMR or Old Mahabalipuram Road. So, all of these places, although within the city limits of Chennai, will record different daytime temperatures at the same point of time because of this concept of microclimate. Because microclimate is dependent on the buildings around the place, the type of buildings around the place. Because now if you look at Mount Road, where there is complete concrete jungle, no greenery, no break in the space, the temperatures would be much higher because of the radiation factor from the re-radiation factor from the paved areas. Now, if you look at places like Adayar or Vandalur, again here what will happen is the temperature will vary drastically because of the percentage of green spaces to the built area. Because of the large green open spaces, the temperature will be at least 2 to 3 degrees lesser. So, when you look at your individual site to finally construct, you need to take into consideration the microclimate of that site. The mini climate that is created around the building can decrease apparent severity of the climate, and hence the work the building must do to make the building comfortable and exterior environment around the building is much lesser. And if this is not handled properly, we will actually increase the severity of the local climate, either make it colder or make it hotter depending on the place we are in. Now, if you look at these photographs over here, you might think how absurd these are. Why is the igloo in the middle of the desert? Why is the igloo in the middle of a road, of a metropolis? But that is exactly what is happening to so many of our buildings within our city. So many of our buildings are direct replicas and copies of buildings from Europe and the Western countries like North America, because that is the corporate face facade of that particular building. And when that corporate moves to a country like India or China, they just plonk that building here. And that's how, as ridiculous as an igloo looks in a desert, that's how ridiculous that building is in within our context. Because now, if this igloo, imagine, was built in the desert, you cannot even build it in the first place because it will melt. But barring that aside, what kind of atmosphere will this create in the desert? Similarly, in a concrete jungle or metropolis scenario. So we need to consider the multivariate condition. What exactly is the multivariate condition? We will look into the details of it. Now, if you look at people-centric buildings are interior conditions like temperature, humidity, air motion, metabolism, clothing, activity, perception, and acclimatization. So, all of these are people-centric factors. Then you have building-centric factors like mechanical cooling, passive heating, envelope conduction. Envelope conduction is what kind of material is your facade made of, convection, radiation, solar gain, what kind of internal lights or equipment you're having, ventilation, all of these are building centric factors. Then site centric factors, we have topography, what kind of terrain is it, orientation, bodies of water, surrounding structures, vegetation, clustering, elongation. So all of these site factors decide the microclimate as well. Buildings also will help us define how this microclimate can be converted to a place that these people can enjoy. Now, moving on to the climatic factors. Natural elements like sun, wind, humidity, we need to take into the consideration of different seasons and their variability at different parts of time in the year. Characters like hot, arid, hot, humid, temperate climates, cold, and we need to take into factors like latitude, longitude, and coastal. Site bioconfiguration. Whatever the found condition of the site upon which we are to consider building, it has to have a climate that is not only dependent upon the general climate of the region, but also the specific climate of the site as it's affected by the surface that covers the ground, available tree cover, that is the size, height, biodiversity, what kind of trees are they indigenous species or have they been brought in, amount of paving, is it concrete paving, permeable paving, what is it, height of the adjacent buildings, all of these decide the bioconfiguration of the site. Now, if you look at this building over here, this is the Institute of Contemporary Art in Boston. Now, Boston is considered a warm and humid climate for most parts, but in winters it can snow and become very cool. And the reason it can be warm and humid during the summers is having the huge lake and water body, which increases the humidity of the site in the summers. So, this building has to have a combination of catering. It should consider the different seasons of the building will face, the different materials that is required to protect the building at different times of the year. So, the bioconfiguration of the building has to be such that it caters to that particular site as against the overall place. Here it's bang on by the river. So, this has more consequences it has to face rather than the buildings which are way farther away. This building is the same, but the site, climate and microclimate conditions are drastically different, and that will impact the success and the comfort by the occupants. So, if you look at this in the original condition, this is how this building is. But if you move it to a hot and arid site, hot and humid site, cold and temperate site, how out of place do these buildings look? When we put these buildings in these images, we are able to sense that they are out of place. But when we are talking about an urban scenario, an urban scale, we forget that we are very close to these temperature zones and we do not incorporate these qualities of the climate and temperature into our design. Now moving on to the urban heat island effect, which all of us are well aware of, especially living in a place like Chennai. We actually have rural areas, commercial areas, and in between the rural and commercial, we have something called the suburban residential. Then we have something called the downtown, or where the commercial business district is. The CBD, the central business district, is referred to as the downtown. Then you have the urban residential, then you have a park or an open space, and suburban residential. So these are the varying spaces we are discussing. And downtown, if you see, that is the CBD, will hit the highest temperature because it causes an urban heat island effect, because the heat all gets trapped because of the maximum material that is used there is concrete. It's concrete pavings, concrete facades, glazing again, which brings in a lot of heat, re-radiation. All of those factors makes the CBDs much hotter spaces rather than the rural areas or the suburban residential areas. So this is the dip and height and increase in temperature that we see in a normal space. Now, how does urban heat island effect actually affect us? You can see this happening in places in Bombay where the CBD is a special area with taller buildings, concrete buildings, hardly any greenery there. So whether you're sited in a city or any suburban space, it actually makes a huge difference, because access to a green space can keep the building cool. The urban heat island effect is caused by too much building, hot roofs, pavement, which increases the thermal mass, and not enough greenery in the cities. So tree cover plays a very crucial role because it actually keeps the sun off the paved areas. The microclimate in urban centers can be very different from the natural sites. Now moving on to bioclimatic design, the cold areas, where winter is the dominant season and concerns for conserving heat predominate all other concerns. Heating degree days greatly exceed the cooling degree days. Here you have the YMCA Environmental Learning Centre in Ontario, where their only way to keep the heat out of the building is their only primary goal. In the summer seasons, when it is hot, which the per period of time we are discussing is only barely 2 months, they can resort to mechanical cooling devices. But when it's 10 months in a year that is so cold, they have to ensure that their dependence on mechanical cooling heating devices is not much, and they are able to naturally warm up the building because of sunlight, and ensuring the sunlight that enters through the day warms up the building for a longer period of time. Now, if you actually look at the rules of bioclimatic design in a cold climate, the first rule is to insulate so that heat gets trapped and does not leave the building. Minimize infiltration. Then you need to insulate and fenestrate for direct gain. That is, your windows have to be there for direct gain of heat. Orient and site the building properly for the sun. Maximize south-facing windows for easier control. Apply thermal mass inside the building envelope to store free solar heat. Create a sheltered microclimate to make it less cold. Now, what are the strategies or the things we need to keep in mind when we are talking about a hot, arid climate, where the very high summer temperatures with great fluctuation predominate with dry conditions. So throughout the year, you have to think about the cooling period more than the heating degree periods. So here again, the reverse is possible. In winters, it does become cooler, but the summers, the energy required to cool the buildings in summer is way higher than the energy that is required to warm the buildings in winter. So this is the traditional house in Egypt that we see. What are the rules that we need to follow over here? Solar avoidance. Let's keep direct solar heat gain out of the building. Let it be only filtered light that enters the building. Minimize infiltration. Avoid daytime ventilation. Promote nighttime flushing with cool evening air. What this actually means is having windows at 2 levels where the hot air actually enters. We need to make sure that windows are given only on top, such that the hot air does not enter the building, rather exits the building at a greater height. We need to achieve daylight by reflectance and use of light non-absorbing colors. You need to create a cooler microclimate by using light or lightweight materials. you need to respect the diurnal cycle. What we actually mean here by diurnal cycle is the nighttime the temperature does drop, the daytime the temperatures are very high. So this steep change in temperature has to be taken into account. But like again we mentioned, where does the maximum energy consumption get utilized? We need to minimize that. Use heavy mass for walls and do not insulate. Where warm to hot stable conditions predominate with high humidity throughout the year, cooling degree days greatly exceed the heating degree days. So this is a house in seaside Florida where we need to make sure the temperature and the climate is cool inside rather than warm, because here the climate outside is very rarely cold such that the building will need heating. Now, bioclimatic design in a temperate area, if you look at the summers are hot and humid and winters are cold. So the topography here is generally flat, allowing for the cold winter winds to just come in the form of northwest cool breezes, and it will flow out from the southwest. So the 4 seasons in these areas are equally long. So if you actually look at a bioclimatic design in the temperate area, example over here we have the Islandwood residence in Seattle, Washington. Here you can clearly see there's a combination of both. You do have glazing, but at the same time a sun shading device has been provided for us to ensure that the summer months are beat. The glazing ensures that in winter the whatever sunlight that enters will make sure the house is warm and kept warm. Here again the paving area is minimized by making sure there is trees and landscaping around. So when you actually look at the correlation between different climatic zones and the microclimates within those zones, we need to take all of these factors into consideration for us to come up with a sustainable environmental design. So we need to study the different types of climates, the site in which the site which we are dealing with, what kind of climate does it entail, and what kind of microclimate does it entail. All of that has to be taken into consideration. So that brings us to the end of this module. Thank you.